Hello, and welcome to lesson 12 of this introduction to calculus with Wolfram U. The topic of this lesson is implicit differentiation. So let's begin with a brief overview of the topic. So far, all the functions that we have considered are in so-called explicit form. So for example, you have the function f, which is defined to be x squared minus x plus 1. And so every time I give you a value of x, you could work out the value of f at that x. So that's an explicit function, but sometimes you have a function that's defined only implicitly. So for example, here's an equation, x squared plus y squared equal to 4, and surely y is a function of x. It depends on x, but it does so in an indirect, implicit way. Now, of course, in this case, you could solve the equation and work out y in terms of x, and you get back two solutions. So really you have two functions of x, and then you could plot them, and what you see is that you have a circle, and the first solution is the bottom of a circle, and the second solution is the top half. So that's, of course, why you need two functions rather than one to describe the problem. So that's the notion of an implicit function, and today what we'll do is to talk about how you can find derivatives implicitly in the Wolfram language. So let's try and do this in one way. So for example, you could take the two functions from the earlier page, from the earlier slide, and try and work out their derivatives separately. So you get back two answers. Now notice that each answer is of the form minus x over y. So that's x, that's y, and both answers have a certain pattern to them. But then what you could remember is that this over here is the kind of the upper branch. So the derivative for the upper branch comes from here. So if you plug in, let's say, square root of 2 and square root of 2, that point, then what you get back is a slope of negative 1 at x equal to square root of 2 for the upper branch. So you can then plot the line, the tangent line, and the circle, and you see that's the correct solution. But of course, this is a very roundabout way of doing things, and what we want to do today is to try and do things in a much more clear-cut, simple way, and that's the notion of implicit differentiation. So the idea is very simple, that whenever you find the derivative with respect to x, you work just as before. But if you have a y anywhere in your expression, then you also make sure to multiply by dy over dx. So for example, here's the equation from the earlier slide, and you have x squared plus y squared equal to 4. So the derivative of 2x squared is 2x, and the derivative of y squared is not just 2y, but it is 2y times dy over dx. That's just the chain rule. Okay, once you've done that, then from the equation, you can solve for dy over dx and find the answers negative x over y, just as we had noted earlier. So that's the technique for doing implicit differentiation, and now I'll show you how we can do it in the Wolfram language. So let's take up the circle again, and there are two ways to go about it. In the first method, what you do is you replace y by y of x. So now the Wolfram language knows that y is indeed a function of x. And then you tell d to find the derivative, and then you solve that derivative for y prime x. And what you get back is exactly what we had guessed early on, namely negative x over y. Okay, now you can plug in values for both x and y. So for example, if you're at the point negative 1 comma square root of 3, then the slope is 1 over square root of 3, and you can then find a tangent and plot both the tangent and the graph, and you see that the answer is correct. So that's the first method. The first method is replace y by y of x. The second method is slightly different. So you start with the equation, but now do not make a replacement, but instead you tell D that y is no longer a constant. And that's what we've done with the non-constants option. And when you do that, you get back an equation for capital D, you solve it, and you get back just the same derivative as before, but now you only have a y instead of y of x. So there are two ways: replace y of x or use the non-constants option. And usually we'll work with the first way. That's a little more natural, but there will be another case where we'll actually try and use the second method, but that'll be in the exercise for the lesson. Okay, so having done this preparatory work, we can now find lots of derivatives with this method. So for example, here is a famous curve called the folium of Descartes. So that's the equation of the curve. You want to find derivative, so you replace y by y of x, work out the derivative, solve for it like over here, and replace x and y with the values that you want to work with, 2 and 2, and you get back the derivative of this curve at 2, 2, work out tangent line, and then you plot the curve and the tangent, and it looks just right. Another example, let's take up the ellipse. So that's like a distorted circle, and you want to find the tangent line at the point 1, negative 3 over 2, square root of 3 over 2. So again, you do the same thing, replace y of x, solve the equation, plug in the values, get back the slope, set up the equation for tangent, and you get back the plot of the ellipse with the tangent line. Okay, from the ellipse we go on to the hyperbola. So that's the hyperbola equation. You want to work at a certain point that's given to you. Again, replace y by y of x, solve for y prime x, plug in the values, and you get back the slope. Write down the equation of tangent, and then you plot the tangent in the curve, and you get back this nice picture. Notice that in all these plots, I'm using the contour plot function to plot the curve itself, while I'm using the plot function to plot the tangent line. Okay, my next example is a so-called cardioid. That's like a heart-shaped curve. It's a pretty difficult equation. So here's the equation of the curve. Replace y of x as before. Find the derivative. It's 1. Write down the tangent equation, and then you plot the tangent of the curve, and you get back this beautiful plot of the cardioid. Another example is the so-called devil's curve. Now it doesn't matter how difficult or easy the equation looks. You do just the same thing. You take the equation, replace y by y of x everywhere. Do just the same as before, but now plug in the correct x and y values. And when you do that, get back the slope. Write down the equation of tangent. So that's the y1, if you like, from your work on straight lines. That's the slope, and that's x minus x1. Okay, and then you plot the tangent and the curve. And notice one thing, that the tangent line at this point might actually pass the curve again, because the curve in this case is like a loop at that location. Okay, so another example is the so-called Kampyle of Eudoxus. That's the equation, but just the same method works. Replace y by y of x, solve, replace values, and you get back the slope. That's the tangent line over here, and then you plot the tangent line and the curve, and you get back the correct solution. So, having talked about derivatives, let's now spend just a few minutes talking about multiple derivatives. So here's an equation. You want to work out not just the first derivative, but also the second derivative with implicit differentiation. So you write the equation down, replace y by y of x, solve and find the derivative. Then you find the second derivative by putting the 2 over here for second derivatives, and you get back the second derivative. Unfortunately, the second derivative has the first derivative in it. But then you can use the earlier step to plug in values. So you plug in the first solution into the second one, and you get back the second derivative now in a much simpler form where it depends only on x and y. Okay, so that brings me to the end of this lesson. So basically, there are two ways to compute the derivatives of implicit functions. In the first one, we express, let's say, y as a function of x. In the second one, you could use the non-constants option. Now, both methods have got their advantages and disadvantages, but overall, the first method is much more closer to what you do by hand, and I recommend that you follow the first method. And of course, we saw lots of interesting curves, and we could plot them and then actually work out derivatives, and contour plot is a really good function for plotting these curves. So that's the end of this lesson, and the next lesson will talk about rates of changes. But before doing that, you should definitely review today's lesson, try lots of examples, and make yourself ready for the next lesson. And of course, we'll also have a problem session before we go on to the next lesson. So thank you very much. I hope you have enjoyed the lesson. I'll stop here.